This is SpaceTime, Series 28, Episode 97, for broadcast on the 13th of August 2025. Coming up on SpaceTime, astronomers track a doomed planet's death spiral, fresh clues about the red planet's past, and a new crew arrives aboard the International Space Station. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers are tracking the death spiral of a doomed planet more than 870 light-years away. The exoplanet, catalogued as TOI 2109b, orbits its host star, TOI 2109, in just 16 hours, and that makes it the closest so-called hot Jupiter ever discovered. The gas giant has nearly 5 times the mass and almost twice the diameter of Jupiter, the largest planet in our solar system. Now, by comparison, in our solar system, the closest planet to the Sun is Mercury. It takes 88 Earth days to complete each orbit, and it has a mass some 6,000 times smaller than that of Jupiter. The host star is a spectral type F orange dwarf. It's moderately larger, hotter and more luminous than the Sun, and is located in the constellation Hercules. The findings, reported in the Astrophysical Journal, show that the planet's extreme close-in orbit will ultimately prove fatal, with the gas giant's orbital period decaying by at least 10 seconds over the next 3 Earth years alone. The study's lead author, Jamie Alvarado Montes from Macquarie University, says the planet's spiralling cosmic death dance is likely to end in one of 3 possible ways. It could be torn apart by the host star's gravitational tidal forces, it could plunge directly into its host star, or it could have its gaseous envelope stripped away by intense radiation, leaving only a rocky core. Alvarado Montes and colleagues reached their conclusions by analysing transit timing data from 2010 through to 2024, using multiple ground-based telescopes as well as NASA's TESS Space Telescope and the European Space Agency's CHEOPS satellite. Alvarado Montes says the findings suggest that some rocky planets in other star systems might also be the stripped cores of former gas giants, a possibility that could reshape astronomy's understanding of planetary evolution. He says that with continued monitoring over the next 3 to 5 years, astronomers will detect orbital changes in the system, providing real-time observations of a planetary system in its death throes.
The Roche limit is like an orbital position where the secondary object that orbits the primary object starts losing its own stability, right? So the self-gravity of the object is overcome by the tidal forces of the primary object.
Yeah, the bit of the planet or the celestial body nearest the primary body is being gravitationally influenced to a larger degree than the bit further away.
Exactly.
So it's literally ripped apart.
So this relationship between the position of the secondary object and the tidal forces of the primary object is general. It doesn't only apply for moons or for planets, but for any pair of bodies where you have them orbiting or interacting very close to each other, and it mainly depends on the relationship of the masses, right? Of the objects, the densities more specifically. So denser objects have the Roche limit closer to the primary object, and less dense objects have their Roche limit like farther away. So, for instance, in the case of Jupiter or of Saturn, you have that icy moons have the Roche limit farther away, and rocky moons, like solid moons, will have the Roche limit super, super close to the planet, to Saturn or Jupiter. And this is a general thing. So it's basically what happened with the system that I worked on, TOI 2109, which is an exoplanet. It's an ultra-hot Jupiter, and it's what people have called like doom because it's spiraling in towards its star. And it's a very, very big planet, like almost twice the size of Jupiter.
And this is, in fact, the nearest hot Jupiter to its host star that we've ever seen.
Yep, exactly. It's orbiting the host star in approximately 16.5 hours, which is the shortest period exoplanet discovered today. Well, the shortest period hot Jupiter, ultra-hot Jupiter. Ultra-hot Jupiters are Jupiter-like planets that orbit their star in less than 1 day. That's the formal definition, but this one does it in 16 hours, so it's quite impressive and well, it will have a lot of consequences.
What do we know about the host star itself?
Yeah. So it's interesting. Like studying these systems is very interesting because all the properties of the objects involved are entwined. So, like you said, if we study this planet, if we study how this planet moves, how long it's going to take for this planet to reach the Roche limit, all of these orbital mechanics, as we call it, really depends on how the properties of the star are modeled and how the properties of the planet are modeled. But also, like not just any model, but models that are based on real data, on observations. And by combining our theoretical models from tidal evolution and the observations that we have for this planet, then we can tell a lot of things about what's going on inside of the star, because the way the planet moves depends on how efficiently the star dissipates energy and also how efficiently the planet dissipates energy, and how this energy is conserved in the system and how it's transferred from the orbit of the planet to the rotation of the star. So it's really this relationship between the spin, the stellar spin, and the orbital motion of the planet, what tells you what's going on in these tidal interactions, right? Because these tidal interactions depend on how efficiently the energy is released from the star or from the planet. And that's how we can learn more about the interior properties of the star, just by looking at how the planet is moving.
And you've come up with 3 likely scenarios. Tell us about them.
Yeah, those scenarios are very interesting. One of the first one that I could mention is that the orbital decay occurs, and as the planetary companion gets close to the Roche limit, and if that decay happens, we could say at a decent rate, like not too fast, then when the planet reaches the Roche limit, then the planet will start getting like obliterated, right? So the planet moves away from its geometrical shape. And once the tidal forces are so strong, so intense that they overcome the self-gravitation of the planet, then you have a planet that is completely disrupted, and you will have all the debris continuing around, orbiting around the star, and well, you don't have a planet anymore, but you have just the fingerprints of what once existed, right? So you just have debris and you just have material orbiting around, or what we call a ring, right? So that's one of the scenarios. It's just the complete disruption of the planetary companion when crossing the Roche limit. But something else that could happen is that the orbital decay is so fast, and it could happen so fast, that could be, trigger, or it could be produced by unaccounted mechanisms of dissipation inside the star or the planet. It could happen that when the planet gets closer in its orbit, it will start actually spiraling in at a faster rate. So as it goes in, if that decay happens very fast, then it could happen so fast that as it crosses the Roche limit, it doesn't slow down when it crosses the Roche limit, but it continues going so fast that it could crash with the star. So the star could engulf the planet, and basically, the planet will also die, will also disappear, but in a different way. Instead of being disrupted before reaching the stellar surface, you have a planet that actually goes head on to the stellar surface and disappears too, but for a slightly different reason, right? So that's a second scenario. And another one that is very interesting and that is being actually quite debated, and we're doing some work on it too, is that if the orbital decay, the spiraling of the planet happens slow, very slowly, so slow that as the planet gets closer in its orbit, then the planetary atmosphere starts getting destroyed by the stellar radiation, via different processes, one of them being photoevaporation. So that's one of the effects that could destroy the planetary atmosphere, photoevaporation, which is basically just the stellar radiation dissociating the molecules in the planetary atmosphere and
it gets spoiled away.
Yeah, exactly. Just like that. So the planet starts losing its atmosphere. And with this loss of material, and taking into account that a giant planet, a gas giant, such as this one, is mainly composed of gas, right? Then a lot of that material will go away, reducing the mass of the planet. Right, so the planet gets less massive, and if that the loss of mass is quite significant, like very, very significant, and reaching, say, I don't know, values of 60% less of the current mass of the planet, then what you have is that the Roche limit gets inner. So the Roche limit gets closer to the star. So what was initially the Roche limit, where the planet could have been disrupted, it's not the Roche limit anymore, because, as I said before, the Roche limit depends on the mass, on the mass relationship of the object. But if the secondary object gets less massive, then the Roche limit moves more. It becomes more interior, like closer to the stellar surface. So allowing the planet to continue its migration without getting disrupted. And at some point, what you can have is that if that material, that atmospheric material, is completely obliterated and blown away, then you end up with a planet whose composition could be mostly like a rocky composition, and you could end up with basically what we could say like a second generation rocky planet, or a proto-rock planet, or something like that. So basically, you have the naked core of what was before a Jupiter-like planet, a gas giant. And this planet has the potential of, and that's based off other studies in the literature, in astronomy, in astrophysics, is that the less massive the planet is, the more stable it is and it will be in its orbit. And less massive planets are less prone to undergo orbital decay. So if you have a planet that is mostly rocky now, then this planet could stay in that orbit because it's less massive and the Roche limit has moved farther away. So it's a very interesting scenario where you could end up with a rocky planet from the obliteration of the atmosphere of a gas giant.
When NASA's Juno spacecraft began orbiting at Jupiter, we discovered we didn't know as much about the internal structure of gas giants as we had previously thought we did. Juno changed our understanding of what's happening deep below the clouds of Jupiter. It means that what's going to be happening with TOI 2109b will be fascinating to see, because we're going to be seeing something we've never seen before.
Oh, yeah, definitely. Right now, TOI 2109 is one of the most interesting systems that we've got, because there's not many. Like, there's just a fraction of all of the planets that we've discovered. It's almost 6,000 now. Other 7,000 awaiting confirmation. This is a very particular system, right? Where tidal interactions are so intense that studying this system further will allow us to make bigger conclusions of how the observations that we collect with different instruments, because we're talking about doing observations using different techniques, such as planetary transits or radial velocity. And it's a way to connect all of these observations with what we know about how these objects evolve and how they affect the whole planetary system, because there's such a massive planet orbiting that close to the star has consequences not only for the planet, but also for other bodies in the system. And at the moment, actually, there is also other studies undergoing studies about trying to detect another planet in the system. So what we will call TOI 2109c, that is the possibility of that there is another planet in the system, an outer planet that is affecting also the way that our planet, 2109b, is moving. So, but to justify these studies, well, we need to keep targeting this system, and we're learning a lot about all the Jupiter-like planet population just by studying this system.
I guess the big question has to be, what's the timetable like? Do we know how long it's going to be before the planet gets so close to the star that it starts to break apart, or have its atmosphere drawn off it, or plunge into the star? Do we have a timetable for that?
Well, yeah, it's an astronomical timetable, we could say, right? Because scales in astronomy are quite big. Sometimes we can't imagine them, right? But yeah, basically the orbital decay of this planet, depending on one of the things that we learned with this planet is that the star that the planet orbits, the host star, might be younger than one we thought before. And it's because the observations match this model of a young host star. So what we learn is that for a young host star, a star of roughly 1,000 million years, the planet will take around 0.5 to 1 million years to get to the Roche limit. Now, those scales are somewhat ridiculous, right, in terms of human time scales.
For me, it's very disappointing. I wanted to see.
Exactly. But there is a way to convert those astronomical timescales into human timescales. And the way we do that is by studying systematically the transits of this planet, and the estimations that we give in our study is that it will take us around 3 to 4 years of consecutive observations of studying transits of this planet to prove that orbital decay is indeed happening. And if we confirm in the next 3 to 4 years that the timing of the transit, something that we call the mid-transit time, that is the time right in the middle of the transit, right when the planet is passing in by the center of the star, if we prove that that timing is changing, and we estimate that over the next 3 years that change is going to be 10 seconds, around 10 seconds. So if we prove that change, that shift in the mid-transit time is indeed happening, then that, and discarding other effects in the system, then that could be a direct evidence that orbital decay is indeed happening and that the planet is approaching the Roche limit just as we predicted. And then, well, more studies, of course, will be done on it. But basically what we need now is just to keep observing this planet, getting more data on it, and see if we manage to detect this shift in the transits. And, well, that will be amazing.
That's Dr. Jamie Alvarado Montez from Macquarie University. And this is SpaceTime. Still to come, fresh clues about the red planet's past. And a new crew arrives aboard the International Space Station. All that and more still to come on SpaceTime. Scientists have identified a new type of iron sulfate on the red planet Mars, which may represent a completely brand new type of mineral. The discovery, reported in the journal Nature, adds new insights into how heat, water and chemical reactions have shaped the Martian surface. Sulfur is common on Mars and it combines with other elements to form minerals, especially sulfates. While most sulfates are highly soluble and readily dissolve on Earth during rainfall, on the dry, cold surface conditions of Mars, these minerals can survive for billions of years and in the process preserve important clues about the planet's early history. And the thing is, each mineral has a unique crystalline structure and properties, including the common minerals gypsum and hematite. Scientists rely on data collected by Mars orbiters to identify minerals on the surface of the red planet and obtain information about ancient Martian environments that would have enabled the formation of those minerals. For nearly 20 years now, researchers have been puzzled by unusual layered iron sulfates with a unique spectral signature. Now, scientists have identified and characterized an uncommon ferric hydroxysulfate phase by combining laboratory experiments here on Earth with Martian orbital observations. The study's lead author is Janice Bishop from the Search for Extraterrestrial Intelligence SETI Institute at NASA's Ames Research Center. She's investigated 2 sulfate-bearing sites near the vast Valles Marineris Canyon system, a huge rip in the red planet's crust, which is the largest single feature on the red planet visible from space. The observations included mysterious spectral bands seen from orbital data, as well as layered sulfates with intriguing geology. The study included a region called Arum Chaos, located northeast of Valles Marineris, where ancient waters drained away towards lower regions in the north, and also a plateau above the Juventa Casmar, a 5-kilometre deep canyon located just north of Valles Marineris. The cliffs in these areas are signs of ancient water channels across the landscape. Scientists found sulfates in just one small low-lying spot, likely left behind when pools of sulfate-rich water slowly dried up, forming hydrated ferrous sulfates. These minerals, including ferric hydroxysulfates, appear as thin, metre-thick layers carrying both above and beneath basaltic minerals, suggesting they were heated from lava or ash after formation. Investigation of the morphologies and stratigraphies of these four compositional units allowed the authors to determine the age and formation relationships among them. Scientists have often observed sulfate minerals throughout the Valles Marineris region, including the rugged landscapes known as chaotic terrains, areas they believe were carved and shaped by powerful floods in the past. As water gradually dried up, it left behind layered deposits of iron and magnesium sulfates, subtle but powerful clues that Mars was once a much warmer, wetter world. In one chaos terrain, which formed within a former impact crater, the upper layers contained polyhydrated sulfates, while monohydrated and ferritic hydroxysulfate layers formed beneath. Each of these three sulfates contains distinct spectral signatures which can be identified from orbit. Now, while the stratigraphy of these three sulfates was initially puzzling, lab tests back on Earth showed that heating polyhydrated sulfates to 50 degrees Celsius winds up producing monohydrated forms, and heating the same material above 100 degrees Celsius ends up producing ferric hydroxysulfates. All this supports the idea that geothermal heat must have caused the minerals to transition. Now, monohydrated and polyhydrated sulfates occur across broad regions of the red planet. However, ferric hydroxysulfates are limited to just a few small areas. So they figure the warmest geothermal sources most likely sat beneath the sites where ferric hydroxysulfates appear today, although more may lie buried under monohydrated sulfates as well. The lab tests looked at how these sulfates all transformed, from zoonite with 4 water molecules per unit cell, to zomolmukite with 1, and finally to ferric hydroxysulfates, which contain hydroxyls instead of water in its structure. Now, it's worth noting that ferric hydroxysulfates only form when hydrated ferrous sulfates are heated in the presence of oxygen. And while the changes in the atomic structure are very small, this reaction drastically alters the way these minerals absorb infrared light, and it's that which allowed their identification from orbit. The reaction requires oxygen gas and results in the production of water. Today, Mars has a very thin atmosphere, and it mostly consists of carbon dioxide. But it still has enough oxygen for this reaction to proceed, and for oxidation of other forms of iron as well. Bishop says the material formed in the lab experiments is likely a new mineral due to its unique crystalline structure and thermal stability. Scientists will now need to search and find it on Earth in order to officially recognize it as a new mineral. Interestingly, this new ferric hydroxysulfate appears structurally very similar to zomolmukite, which is a monohydrated ferrous sulfate mineral. But ferric hydroxysulfate form more easily than zoonite, which is a tetrahydrated mineral. This transformation from hydrated ferrous sulfates to ferric hydroxysulfates only happens at temperatures above 100 degrees Celsius, and that's much hotter than what Mars usually experiences on its surface. It's thought that the sulfates at Arum Chaos and Juventae, including the ferric hydroxysulfates, likely formed much more recently than the terrain in which they occur, possibly during the Amazonian period less than 3 billion years ago. The study reveals that heat from both volcanic activity at the Juventae Plateau and geothermal energy below Arum Chaos can transform common hydrated sulfates into ferric hydroxysulfates. The findings all suggest that various parts of Mars may have been chemically and thermally much more active more recently than scientists previously believed. And that is offering new insights into the red planet's dynamic surface and its potential to have once supported life. This is SpaceTime. Still to come, a new crew arrives aboard the International Space Station, and later in the science report, a new study shows that it's your mother's fault if you end up fat. All that and more still to come on SpaceTime. NASA's just delivered 4 new crew members to the International Space Station aboard a SpaceX Dragon capsule. The spacecraft Endeavour docked with the orbiting outpost's Harmony module Zenith port 15 hours after launching aboard a Falcon 9 rocket from Launchpad 39A at the Kennedy Space Center at the Cape Canaveral Space Force Base in Florida. A launch attempt the previous day had to be scrubbed due to bad weather. The new crew, consisting of 2 Americans as well as a Russian and a Japanese astronaut, will spend at least 6 months aboard the station, replacing colleagues who had already been up there since March. Right now, NASA is looking at increasing space station stays from 6 to 8 months in order to cut costs. That's a move already being adopted by the Russian Federal Space Agency Roscosmos. The decision comes as SpaceX is closer to certifying its Dragon capsules for longer flights, which means the newly launched crew could remain on station until April 2026. NASA's also looking at going back to using smaller 3-man crews for each transport rather than the current 4. Again, it's a move designed to cut costs. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with the Science Report. A new study claims consuming 3 servings of fries a week is enough to be linked to a 20% increased risk of developing type 2 diabetes. But eating the same quantity of potatoes but cooked in other ways, such as boiled, baked or mashed, does not substantially increase your risk. The findings, reported in the British Medical Journal, also found that swapping out potatoes for whole grains cut your diabetes risk, but swapping them out for white rice actually increased the risk. The findings are based on data from 3 previous large US studies, including a total of more than 205,000 people. They'd been asked to complete detailed food questionnaires every 4 years for almost 4 decades. During this period, 22,299 people were diagnosed with type 2 diabetes. Now, although this type of study can't show cause and effect, the authors say it all adds to existing evidence that whole grains are effective in helping prevent type 2 diabetes. Well, if you're getting fat, chances are you can blame your mother. A new study has shown that your maternal genetic background plays a greater role in determining whether you'll become obese. A report in the journal PLOS Genetics looked at the body mass index measurements, diet and genetic data of more than 2,500 mother, father and child trios. The authors found that a mother's body mass index may be especially important for determining the child's eventual weight. A new study claims that including just a few emojis in your texting could end up making a relationship stronger. A report in the journal PLOS One claims the use of emojis in messaging improves how people feel others are responding to them, and therefore helps you feel closer and more satisfied in your relationships with them. The authors worked this out by asking 260 people aged between 23 and 67 to imagine they were the ones seeing a series of text images that either included or lacked emojis. They were then asked to focus on their partner's replies. The participants ended up rating partners who used emojis as being more responsive than those who sent text alone. And this was positively linked to their closeness and relationship satisfaction. Interestingly, the authors found no difference between using face and non-face emojis, suggesting that it's the presence and thoughtfulness of the emojis themselves that matters rather than the type. Google are about to offer their advanced AI study tools to college students in selected countries for free. With the details, we're joined by technology editor Alex Zaharov-Reutt from TechAdvice.life.
Google's going to launch a new phone soon. We don't have all the details yet because it's not public. Plenty of leaks, but we have to wait for the keynote to see what's real. But what we've got is Google bringing, as they say here, the best of AI to college students for free. Now, this is in the US and Indonesia and Brazil first, but they're giving college students access to their most advanced tools and also their new guided learning mode. They're giving $1 billion to support AI education and training programs and research in the US. It'll roll out to other countries, I guess, as well, but they'll get expanded access to Gemini 2.5 Pro, where you can ask any question, you can upload images, provides quick homework help. You also get the deep research capability. This is where you can custom research reports just by asking, you say what you want to know about and put sort of some detail. And then you get this multi-page report from hundreds of sites across the internet. And also there's this thing called Notebook LM. I love this. I use this myself. You can download it right now. It's free, but there's also a pro version. And what you do is you put in any text or a PDF or a website, page on a website, but you can copy and paste like your own thoughts, your own notes or notes from school or from wherever it might be. And it creates not only like a summary, but it creates a 2-person podcast. They do this incredible job of creating this podcast with all the important points highlighted and this banter and chatter between the two of them. There's also VO3. You can transform a text or a photo into an 8-second video, and higher limits using Joules, which is a coding agent. You also get 2 terabytes of storage. So Google is really trying to make themselves indispensable to students, giving them lots of space. I mean, obviously they hope in the future they'll pay the money to keep using it. But the AI stuff that Google is doing is pretty much outstripping a lot of other players in the industry. Apple's AI is nowhere near as advanced, although they're going to spend a lot of money to fix that. And of course, ChatGPT and Microsoft are working together against Google. But AI, it's just the beginning, and we're seeing the big players really bring out the big guns to help people and try and capture hearts and minds and future wallets.
iOS updates? What's happening?
Apple launched the iOS 18.6 updates, and this is the update for its current released version of the iPhone OS. But they also did the same for macOS 15.6, iPad OS. Basically, these updates are not really introducing any new features of note. It's fixing bugs, closing security vulnerabilities. So please check all your Apple devices, and in fact, check every device in your house. It's the mantra that I always talk about. It's the sad reality of living in the 21st century. You've got to check for updates. Your 50-year-old fridge, you never had to worry, but modern devices, you do. So please check. And iOS 26 is coming in September. Been using the beta version, loving it. Everyone's going to get a chance to play with it in just a few weeks.
That's Alex Zaharov-Reutt from techadvice.life. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.